Hello everyone, I'm Chris Rickett, a senior programmer at Dlala Studios, and in this session I'll be covering the problems and solutions that we discovered during the development of Battletoads and its array of genres. In today's session we will be covering a quick overview of what is in Battletoads, our depth of field requirements and how we achieve them, the culling system that we implemented to reduce CPU load, an overview of how we managed our visual effects throughout Battletoads, as well as going over how we had to develop a supplementary visual effects system specifically for one of our game modes, the shoot 'em up. Battletoads is a lot of things, but for this talk, Battletoads is going to be a collection of game modes, with each mode having a set of unique requirements, as well as requirements that they share. These game modes include a brawler, 3-player minigames, turbo bikes, a mode where you grind along splines, more minigames, a shoot 'em up, throw in a 2D platformer, some more minigames for good measure, and of course a few boss fights. The observant among you may realise that there are fewer than 11 bullet points. I confess I had to combine and even cut a few just to make sure they fit on one slide. So let's take a look at our first hurdle. Early on, we knew that we wanted depth of field. It gives a great sense of distance and scale, as well as a clear visual separation between the gameplay and the background. It also allows us to reuse assets for both the foreground and the background, avoiding the need for artists to bake in any blur and limiting those assets to a specific distance. So why doesn't this work out of the box with the built-in renderer and post-processing stack version 2? The depth buffer is what allows the depth of field effect to read the distance of an object from the camera. Sprites are treated as transparent, and transparent objects do not write their depth to the buffer. If we want our sprites to blur through depth of field, we will need them to render using a custom shader. The shader will need to implement an alpha cutoff, you'll have to have Z-write turned on, and the Z-test will need to be set to less than or equal. For more information, check out the Unity manual. There's a page called Shader Lab Culling and Depth Testing, which goes into more detail. Let's take a look at the steps that we took to get the background rendering. We added a second camera and a new background layer for it to render. The new camera was parented under the existing camera so that their transforms remain in sync. The depth of the background camera needs to be set to a lower value than the main camera so that it renders first. Add a new post-process layer to the background camera with the profile set up to only apply depth of field. No other effects will be applied at this point. All of our background objects needed their layers set to the new background layer so they're rendered only by the background camera. We then remove the new background layer from the main camera to prevent those objects from rendering twice. Finally, we remove the depth of field effect from the main camera's post-processing profile. The next steps we have to do in code. We need to reuse the results of the background camera. So to do that, we set it up to render to a texture that we can later use. Here we define a component and create the render texture, assigning the camera. We give the render texture a name so that we can identify it easily when we're debugging. The render texture is released here in onDestroy. Now let's look at how we can add some methods to add and remove a command buffer. We want to copy the results from the first camera and render it to our second camera. To do this, a command buffer is created. We add a blit instruction, then we give the command buffer a name so that we can identify it within the frame debugger, and then we add that buffer to the main camera. Disabling the effect involves unassigning the render texture, removing the command buffer, and releasing the command buffer by clearing it and subsequently setting its reference to null. Now what does this look like in action? Here we will take a look at some screenshots taken from the frame debugger. The first shot shows the objects that render to the depth buffer during the background camera's depth pass. The second shot shows the result of the background camera's full render after post-processing. This is the result of what is in our render texture and will finally be blit across to the main camera. In the final shot, we can see the main camera rendering over the top of what was created to produce a final image. So what did we achieve? Firstly, it worked. We managed to get the background sprites rendering with depth of field effect, giving a sense of scale and distance to the scene. It was easy to separate our render using the two cameras' render masks. Because we used a render texture, we can now control the resolution of the background. This also meant that by setting a constant resolution to the render, we could get a consistent effect across different resolutions and platforms. After some initial profiling, it was clear that we had more components performing their behaviour than we required. Things further into the level, for example, were calculating their positions or updating their view. We needed some kind of culling system. We found that Unity's sprite skin component did not have culling implemented. This has since been added, but at the time we needed to handle this ourselves. We had objects performing checks that could only be possible when the player or the camera were close. These are needless calculations. We had other things such as moving objects that updated using a rigid body to follow a path. These physics calculations we only need when the player is around. Otherwise, the rigid body could be slept and we could maintain its position elsewhere. Overall, we wanted to reduce the number of component computation to what was on or nearly on screen. After a quick internet search, I found Unity's Culling Group API. The documentation states, Culling Group offers a way to integrate your own systems into Unity's culling and LOD pipeline. Perfect. This is exactly what we wanted, but how are we going to use it? We only wanted to cull using static spheres. This simplifies the implementation. The Culling Group spheres can be updated, but we won't need that. The Culling Group API uses an index to identify which sphere is the subject of the event callback. This means we can easily store a synced array or a dictionary to look up our instances. If we are simply using an integer to look up an object instance, we can easily make the object type an interface. That way we can easily extend any mono behaviors. We use Cinemachine, and as a result, we only ever had one camera frustum that we were worried about. This meant that we only need one culling group. So, what is it that we want from our culling system? When the level was loaded, we want to be able to grab everything that is potentially cullable and put it into some kind of collection. As mentioned earlier, by using an interface, any existing mono behaviors can be extended with the cullable functionality. The Culling Group API uses an object for a group, so we'll need to create one, set it up, and subscribe to its event so that we can inform our interfaces. When we get the callback fired, letting us know that a sphere has changed state, we'll then need to look up the corresponding ICullable and let it know. This was pretty easy to get the initial system set up, and although our system ended up with a few extra functions, I will go through a stripped down version now. Firstly, we'll define our interface. It's super simple and designed to serve only two purposes. Firstly, it defines a sphere through its position and radius. It also has two methods that we use to notify it and allow it to become activated or let it know when it should become dormant. In our production implementation, we used a scriptable object to store all of the cullable instances. But to simplify this implementation, we simply use a static list. There is an incredible talk by Ryan Hipple called Game Architecture with Scriptable Objects from back in 2017, which covers this concept along with many other helpful use cases for scriptable objects. I would strongly recommend this to anyone that hasn't seen it. Next, we move on to the example cullable mono behavior. We implement the position and radius properties that define the sphere, exposing them in the editor. At this point, we could easily add a gizmo. The two notification methods here are left empty, but this would be where you would implement your specific behavior. An example of this could be as simple as disabling a component or setting the component's game object to inactive. You can also see here that we're adding this component to the static list in awake. This leaves the start method clear for our system to grab all the instances and process them. Okay, so our level is loaded. Our list is populated with ICullable instances. Now we need to create our culling group to do all the heavy lifting for us. We need to add a few things to our culling system component. The create group method you can see here creates a culling group object, passes in the main camera, and registers to its callback. It then iterates all our known cullables, creating a bounding sphere for each and adding them to a dictionary for later lookup. Finally, it passes in the bounding spheres into the culling group and clears the cullable list. With the culling group set up, all that remains for us to handle is the callback that we previously registered. The event payload provides us with all the info that we need. The index of the sphere that we can use to look up the ICullable instance, the two booleans to check whether the sphere has become visible or become invisible. All that's left for us to do is call the corresponding method on the interface. Right, let's see some examples from Battletoads. We used our system to cull playable director components that animated parts of the level, moving hazards that used a rigid body 2D component, and skinned components that were used to animate a lot of background props. So let's have a look at these in action. Here we can see a playable director that controls these three NPCs. A cullable component maintains the current time for the playable director. It only updates the time on the director and evaluates it when the cullable is on screen. When they become off screen, you can see that the current time is no longer updated. The component internally keeps a timestamp for the current time. The animators that the director controls are disabled and enabled by the cullable implementation. In this example, we have a number of hazards moving along a path using a rigid body. When the character progresses and the hazards become off screen, the rigid bodies are set to sleep. Their target position on the path is still calculated, but we avoid the potentially expensive physics simulations. When the hazards become on screen again, they set the rigid body's position to the target position and then resume simulation. In the final example, you can see a number of skinned foliage sprites. The animators are already set to cull automatically, but the sprite skin component itself does not. So, we enable and disable the component within the cullable implementation when it becomes off screen. Here you can see all of the sprite skins being disabled, and they all stop and resume back to their original sprite form. When they become on screen again, the sprite skin component is enabled and they resume their animation. The Culling Group API allowed us to quickly implement a simple and performant culling system. By using an interface, any mono behavior that was identified as being an issue or something that could be optimized was easily fixed. This included Unity components that were missing culling solutions or that we required more control over how and when they were culled. Finally, the huge bonus for us was that we could see all of this happen live in the editor's scene view. This was ideal for getting a quick feel for how many entities were being updated. For Battletoads, we required a visual effects system that could be reused for multiple game modes. We didn't want any spikes from instantiation or garbage collection, so we wanted all of our effects to be instantiated during loading and utilise pooling. Components and systems should be able to easily request an effect that is spawned and managed for them. Some effects we may want to follow an entity until they have played out. For example, we might have some debris falling from a character after they've smashed through a wall. The effects will need to be recycled for later use, and it would be useful to be able to monitor the number of active instances and their pool sizes. We would also want to be able to set their default pool size per effect. There is likely to be only 1 or 2 jump effects, for example, compared to a lot more that we may be required for an AoE hit effect. So here we have an effect created by the visual effect artist. You can see how the effect is composited from a number of subparticle systems. We want to wrap this effect in an object that we can then reference. We use an abstract monobehavior for the visual effect with limited methods defined for things such as play, stop, and update position. The abstract base class allows us to reference any subclasses as a serialized field. A scriptable object defined here is used to house and serialize the reference for each visual effect. This allows the visual effect assets to be created before there is any visual effect prefab set up. We also expose a configurable pool size within this object. Because this is a scriptable object, it can be serialized into any component that we want to instantiate and use an effect for. We want to know what visual effect assets are required so that we can pre-instantiate all of our pools during loading. To do this, our components have a serialized reference for every visual effect that they will need. They also have a reference to a scriptable object that contains a list which they add their effects to. In Battletoads, we managed our own initialization functions, but this could easily be done in Awake. A manager can then read the list, in Start for example, and pre-instantiate the contents of all the pools. In Battletoads, we did this over a number of frames so that we could have a smoother loading. Now, with this list populated, it's time to see just how the Visual Effect Manager would use it. The manager's responsibility includes creating the pools with a default number of instances and storing them in a dictionary so that they could be retrieved quickly and efficiently later. Upon receiving a visual effect spawn request, the manager looks up the pool for the given effect, pops an instance from the pool, and spawns it at the requested position. The manager is also in charge of updating the active effect instances and recycling the instances when they've finished, returning them to their respective pools. The benefits to having one component manage a system is that you can show some really nice information in its editor. We expose the pools to the editor so that we can draw every pool and how many instances are in each. We also show the active instances to quickly check how many instances are currently active and to check that they all clean up. In the game, we allow the pools to expand if they need to, but we do throw an error in the editor because we don't want this to happen in the build at runtime. Each pool has access to the current pool size and its original pool size. This means that we can add a tool to quickly overwrite the original pool size to the current expanded size at runtime. We also added a button to select all the active instances within the hierarchy so that we could quickly find any issues. So what did we end up with? We had no instantiation or destruction of any game objects during gameplay. Everything was done in the loading screens. A component only required a reference to the effect that it wanted and the event to request it. In the absence of a manager, there were no errors. The tools were simple to create and maintain, and they allowed us to quickly find any issues during development. However, we encountered an issue in our Shmup levels. These levels had a lot of ships on screen at one time. Each enemy could potentially fire a lot of projectiles. The players fire a lot of quick projectiles, but also they can collect power-ups that increase their fire rate or fire pattern. The current implementation is simply too CPU heavy due to the sheer number of particle systems required for all of the projectile impact effects. If we quickly recap the anatomy of a visual effect, you can see there are a number of subparticle systems used in a single effect. In this example, there are a total of 14 particle systems used to create this effect. The problem here is that each duplicate instance scales with the number of particle systems required. If we have 4 effects, each containing the same 8 particle systems, that means we need 24 particle systems. What if we change the way we think about these effects? We want a group of particle systems. We know that much. Each particle system will emit a few particles. There's likely to be required a small variation in the number of particles that they spawn. What if we emit these particles on each system ourselves? If we disable the emission module on our particle system, we can then reference it and manually fire a random range of particles at a given position. Here you can see within our play method that we get the emit parameters, pass in a position, and then emit a random number of particles. Here is an example implementation where we combine the particle emitters that you saw previously to create a more complex effect. This component's play method can now be called to play instances of an effect, reusing the same systems for each. So let's take a look at what kind of effect that had within Battletoads. If we take a weapon power-up that allows the player to fire 17 projectiles in a spread that can impact within a very short period of time, over 240 particles are used to display all of these impact effects. This used to use 68 particle systems to achieve this effect. But now with the restructured system, we only need 5. So what did this mean for the game mode? No animations were removed to make room for the visual effects. In fact, some enemy ship animations ended up more complex than before. We managed to play an effect for every impact. Before, we were ignoring impacts that were within a certain cooldown period on the same target to try and limit the number of concurrent effects. Without removing any content, we managed to achieve our 60 frames per second target. So what did I learn? Don't reinvent the wheel. Are there any solutions already available from within Unity that you can leverage, even if you end up using it in an unconventional way? Scriptable objects are very powerful. Although I only glossed over how we use them, they feature in almost every one of our systems. There are a number of very good talks out there on scriptable objects. Unforeseen issues that arise later in development can feel like a heavy blow, but don't be afraid to redesign a system and have fun doing it. Check out the Unity documentation for more information on the subjects covered, and there are some really informative talks on scriptable objects. Thank you for attending this Unite Now session on the technical trials of making 11 game modes. I hope you've learned a lot to help build your Unity skills and advance your own projects, and feel free to provide us with feedback. Finally, be sure to check out the Unite Now page for other sessions that are sure to inform and inspire you.